So in this video, I propose to do trigonometry in spherical and hyperbolic geometry exactly the same way I did it in Euclidean and Minkowskian geometry. Let's get started. The secret of doing this is to find the direction vectors at each vertex. In Euclidean and Minkowskian geometry, these two vectors were equal and opposite to one another. But now they are not equal and opposite three-dimensional vectors. Once I found these, I'm going to use the two direction vectors at each vertex and take their dot product to determine the angle there. And once I've done that, I found a way of expressing the cosine of each angle in terms of lengths. That's the law of cosines, which works in every geometry. And then, you guessed it, I'm going to replace sine squared x by 1 minus cosine squared x, plug in my formula for the cosine of each angle, and I will end up with the law of sines. And finally, having done the general triangle, I'm going to specialize to the case of a right triangle. This is the opposite of the way trigonometry is usually done, where you start out with right triangles and move on to arbitrary triangles. So here's a nice spherical triangle. Boston is far west in the Western Hemisphere at vertex B. Here is Athens at vertex A, and to get a good big triangle, we'll include a place that the ancient Greeks never knew about, namely Cape Town. So when I talk about the angle at vertex B, I mean the angle between the two direction vectors, one from Boston along the Great Circle toward Athens, and one at Boston along the Great Circle toward Cape Town. Since I haven't plotted the x-coordinates, the angle between the vectors that I actually display in the diagram is a little bit misleading, but the angles are shown correctly on the diagrams. Okay, let's get busy calculating distances and angles. To get the distance from Boston to Athens, which is measured in radians, of course, I just take the arc cosine of their two position vectors. The direction vector is a little bit trickier, but I say to get the position vector at Athens, I take the position vector at Boston times the cosine of the distance in radians from Boston to Athens, and add on the direction vector at Boston times the sine of that same distance. And when I solve this for v, I get a for Athens minus b for Boston cosine c over sine c. If I want Boston to Cape Town, I do exactly the same thing, except I replace Athens by Cape Town, and the cosine and sine of side C with the cosine and sine of side A. Once I've got the vectors v and w, I can take their dot product, and the arc cosine of that dot product is the angle between the two direction vectors at Boston. And when you multiply these together, interesting things are going to happen. A dot C is going to give you something that involves the cosine of side B. B dot C and A dot B will multiply cosine A and cosine C respectively. So I'll get a couple of terms involving cosine A, cosine C with a minus sign. But then this last term gives me cosine A times cosine C times the dot product of B with itself. And since B is a unit vector, I'm going to get the same thing with a plus sign. So here's the law of cosines for spherical geometry. The cosine of the angle at vertex B is the cosine of the angle at the opposite side minus the product of the cosines of the other two sides divided by the product of the sines of the other two sides. Now, what happens if we make the sides of this triangle small? You all know If you draw a triangle on the floor, strictly speaking, it's a spherical triangle, but it looks for all the world like a Euclidean triangle. And so if the side lengths of our triangle are small, we expect to get back the results from Euclidean geometry, which look quite different. The unit of length on the Earth, 1 radian, works out to about 4,000 miles. So small is small compared with 4,000 miles. And in that case, we can approximate the sine of b by b and the cosine of b, not by 1, that's too crude an approximation, but by 1 minus b squared. So if I take the law of cosines in spherical geometry, replace cosine b by 1 minus b squared over 2, cosine A and cosine C by 1 minus a squared over 2 and 1 minus c squared over 2. Throw out the term involving a squared c squared over 4 and move the 2 into the denominator. What do you know? I get back the law of cosines for Euclidean geometry. Euclidean geometry is the limiting case of both spherical geometry and hyperbolic geometry. Now let's do the law of sines. No geometry, lots of messy algebra. I want to compute sine squared b, that's 1 minus cosine squared b. I have a formula for cosine squared b in terms of the cosine and sine of various sides. And here it is. I multiply it all out. And here it is. And this is looking pretty good, except A and C are showing up in the denominator. But where is B? No problem. I'll divide by it. And when I do that, what do you know? The numerator involves A, B, and C in a thoroughly symmetrical way. So does the denominator. And I conclude that if I had chosen to calculate sine squared of capital A over sine squared of little a, or the same thing involving capital C and little c, I'd have got the same result. And presto, again, I've got the law of sines for spherical geometry. Since spherical geometry uses both elliptic angle measure and elliptic length measure, I have ordinary trig functions, and the law of sines involves sines of angles and sines of the distance of the opposite sides. All these angles and all these distances being measured in radians. So now let's look at the special case of a right triangle. And if I put the right triangle so that vertex C is at Acra Ghana, where the prime meridian and the equator meet, the right angle at C really looks like a right angle. But when I draw the diagram, the hypotenuse looks distinctly curved. And you look at this right triangle and say, something is wrong. These two angles don't sum to 90 degrees. That's correct. In a spherical triangle, the sum of the three angles is greater than 180 degrees. Here are all the side lengths correctly measured, all the angle lengths correctly measured. And when I look at the right angle at C, I say, well, the cosine of the angle at C is always the cosine of the length of side little c minus the product of the cosines of the lengths of the other two sides over the product of their sines. But the cosine of a right angle is 0. That means the numerator must be 0, and the Pythagorean theorem says the cosine of the hypotenuse is the product of the cosines of the other two sides. That looks quite different from Euclid, but we know that if the triangle is small, this has to reduce to the Pythagorean theorem as you've seen it in Euclid. So what does right triangle trigonometry look like in spherical geometry? Well, here's the law of cosines, and now I'm applying it to one of the acute angles of my right triangle, the acute angle at A. Since this is a right triangle, the Pythagorean theorem holds, and I can use the Pythagorean theorem to replace the cosine of side A by the cosine of side C over the cosine of side B. And after a little bit of algebra, I get the cosine of angle A is the tangent of the length of B over the tangent of the length of C. And you say, this looks pretty good to me because for small side lengths B and C, the tangent of the side length is roughly equal to the side length. So the cosine of angle A is approximately the length of the side adjacent over the length of the hypotenuse. If I take the law of sines and set the sine of capital C equal to 1, because capital C is a right angle, again, I get the sine of capital A is equal to the sine of side A, sine of side C, and for a small triangle, that's just A over C, side opposite over side adjacent. But you'll notice that the cosines are given in terms of tangents and the sines are given in terms of sines of side lengths. So it's no longer true that the cosine of angle A is equal to the sine of angle B. Why is that reasonable? Because this is no longer Euclidean geometry. The angles no longer sum to 180 degrees, and the cosine of angle A is no longer equal to the sine of B. But in a very simple way, one of these is a ratio of tangents, the other is a ratio of sines. Now let's switch to hyperbolic geometry. This is a thoroughly invented triangle, but I'm going to call the vertices Boston, Athens, and Cape Town nonetheless. I've drawn the diagram in the Klein model, so the sides of the triangle are represented by Euclidean line segments. Don't be fooled. These are hyperbolic lines. What do I mean by the angle at vertex B? I mean the angle between the direction vector along the hyperbolic line that goes from B to C and the direction vector along the line that goes from vertex B to vertex A. And don't be fooled. This angle has a hyperbolic measure of 37.5 degrees, but that's not its Euclidean measure. So we take what we've done for spherical geometry and replace trig functions by hyperbolic functions everywhere. So that means to get the distance from Boston to Athens, the hyperbolic distance, I take the hyperbolic dot product of the position vectors B and A and form the inverse hyperbolic cosine to get the distance. I can find hyperbolic Athens from hyperbolic Boston by taking the position vector for Boston and multiplying by the hyperbolic cosine of the hyperbolic distance and adding on the position vector, the direction vector, times the hyperbolic sine of that distance. And when I solve this, I get a nice looking formula for the direction vector V. Replace Athens by Cape Town, I get the other direction vector W. If I want the angle at Boston, since this dot product is going to be negative, I have to change its sign before I take the arc cosine, but that gives me the angle at Boston. And so when I put everything together, I get the law of cosines for hyperbolic geometry. It looks just like the law of cosines for spherical geometry, except that the sign is reversed in the numerator and all the functions are hyperbolic rather than ordinary trig functions. Again, I can go to the limiting case where the side lengths are small, and this time I approximate the hyperbolic sine of B by B, but the hyperbolic cosine of B is greater than 1. It's approximately 1 plus B squared over 2. And when I substitute these approximations into the law of cosines, what do you know? I get back exactly the law of cosines for Euclidean geometry. So Euclidean geometry, as you can see, is the limiting case both of spherical geometry and of hyperbolic geometry. You can guess how I'm going to do the law of sines, and you're going to be glad you don't have to do the messy calculation. To get sine squared b, I form 1 minus cosine squared b, for which I've got formulas because I know the law of cosines. After I construct sine squared b, I discover that there's something involving b missing from the denominator. I divide by that, and yet again, I get a formula that involves a, b, and c symmetrically in both the numerator and the denominator, and therefore I conclude I would have got the same formula had I used a or c instead of b, and I've got the law of sines for hyperbolic geometry. But notice here, since we're using elliptic angle measure and hyperbolic length measure, the ratio in question is the sine of the angle, ordinary trig function, over the hyperbolic sine of the hyperbolic length. Now we can specialize again to a right triangle. And in the Klein model, if I have two lines intersect right at the center of the circle, a right angle actually looks like a right angle. So here is a hyperbolic right triangle with all the hyperbolic angles and hyperbolic lengths correctly labeled. But the angle at C is a right angle. So the quantity given by the cosine of C must be equal to 0, and that means we've got the Pythagorean theorem. It's exactly the same as the Pythagorean theorem in spherical geometry, except we use hyperbolic cosines instead of ordinary cosines. Now let's specialize to the case of a right triangle and look at the cosine of one of the acute angles, say A. Here's what the law of cosines says it is. But in this case, we've got a right triangle. So again, I can use the Pythagorean theorem and say the hyperbolic cosine of A is the hyperbolic cosine of B over the hyperbolic cosine of C. When I put that in and do a little bit of trigonometric manipulation, I discover this time the cosine of angle A is the ratio not of ordinary tangents, but of the hyperbolic tangents of the sides that intersect at that angle. For the law of sines in a right triangle, I just note that the sine of a right angle is equal to 1. So sine capital A over sinh little a is sine of capital C, which is 1 over sinh C. I solve this for the sine of A, and I get a ratio of hyperbolic sines. I can do the same thing for the sine of angle B, and you'll notice yet again the cosine of angle A is not quite equal to the sine of angle B, because in one case I have a ratio of hyperbolic tangents, in the other case a ratio of hyperbolic sines. The fact that the cosine of one acute angle is equal to the sine of the other is another peculiarity of Euclidean geometry. Okay, at that point I have come to the end of spherical and hyperbolic trigonometry, and it's my understanding that had you been Harvard math concentrators in the 19th century, this would have been what finished up your mathematical education after 4 years. And what do you know? We've done this all in just a few weeks, and we have as a special case hyperbolic geometry, which may have been well known to the leading mathematicians of the 19th century, but which I strongly suspect was never taught at Harvard in that era.